Okay, so we're in the middle of talking about caches, and our two friends here, Hans and Fritz, are doing 6004 jokes. But there's a lot of truth to what they're saying, which is that in many instances, we sort of need to do some engineering where we have a slow thing that we need to make faster. In our case, our problem is that this main memory system down here, okay, is in fact tends to be slow, and in modern machines it probably has a cycle time that's 1 or 2 orders of magnitude slower than the rate at which we want to run instructions. So it's sort of puzzling that if I have to fetch an instruction every cycle, how do I do that when memory might take 100 cycles to actually return a value? So that's the engineering problem we're trying to solve. And the way we did that is we interposed this yellow box, a cache. And what the cache does, it enables the memory system, think of the cache as, if you will, part of the memory system. Anyway, it's the thing that the CPU talks to when it wants memory data. The cache is able to respond quickly to a certain small number of memory requests. And if we do the engineering correctly, we can parlay the ability to respond quickly to a small number of requests and to a small number of addresses, is what I should have said, to something that will work quite well, because as we observed last time, if we look at over a certain span of time the list of addresses that a program accesses, we'll discover, in fact, that it often is asking for the same address again and again and again. Not right in a row, but if the machine is in a loop, is going to be fetching the instructions that are part of that loop again and again and again, each loop iteration, and there's where the cache can really shine. So what we're going to do today is to a little bit remind ourselves just about sort of the basic functionality of caches, and then we're going to look in detail at a bunch of architectural decisions, which is what us engineers need to actually make when designing the cache circuitry itself. So remember, associated in a cache, this is sometimes referred to as an associative memory, because you address it not by location, okay, but by some part of the contents of that location. People sometimes call it a content addressable memory, because each location in the cache has both an address and then it's remembering the contents of memory at that address. But both the address and the memory contents are remembered, and what we need to be able to do is to quickly, or as quickly as we can, or as inexpensively as we can, that's part of the trade-off we'll talk about today, is to be able to locate a particular address, the contents of a particular address. And so conceptually we search the cache, and we'll talk about how that search works, review how that search works again in just a second. And if we find it, we respond with a hit, and that happens very quickly, sort of on the scale of a single instruction time in the CPU. If we're writing to a memory address, we can simply say, oh, we have that in the cache, I'm just going to update the contents of the cache. However, if we don't find it in the cache, that's a cache miss, and what we need to do then is to go off to main memory. So alpha% of the time we will hit in the cache, that's called the hit ratio. The rest of the time, which we hope will be only a small percentage, 3 or 4% at most, we'll actually have to go off to main memory. And our goal today is to pick our architectural parameters, turn the knobs as we choose the different sorts of values for how we can do the engineering of the cache, so that we can expect that hit rate to be quite high and that the miss rate is quite low, and then we'll have to go off and fetch. On a miss, everybody has to sort of sit around and wait. Now, we use caches a lot. We happen to be talking about a memory system for a CPU, but for example, your browser uses a cache because it can take a long time to download complex images and web pages from the host, and to the extent that it can, it checks to see if, do I already have this information? And if so, it will go off and simply fetch the information out of a local copy. That's its cache. And so the first time you look at a web page is often quite slow. In other words, you can actually sort of drum your fingers while waiting for all the images and stuff to load. But often when you come back to the web page, it's almost instantaneous. And that's because almost all of the information, okay, is coming now from the cache. And there's a little bit of a protocol the browser can use to check back with the system, has anything changed? And if the answer is no, it says, okay, I'm just going to use what's in my cache without having to re-download tens and hundreds of thousands of bytes of images and text. Okay, so caching is your friend, particularly when you're faced with something where there's a long latency that you have to sort of deal with, and what you want to do is to hide the long latency, and whenever you can, do something much, much quicker. So here's the 4 engineering things we're going to be looking at. We'll be looking at associativity, and I'll remind you what that means in just a second. A replacement strategy. So I shall say a little bit more. So associativity is about figuring out how many different places an address can live in the cache. So it could only live in one place, it could live at any line in the cache, and that choice, we can, the more places that live in the cache, the more expensive the search can be. Obviously, if a particular address can only be in one place in a big cache, we only have to look just there. If it can be any place in the cache, we have to invest in the hardware to look everywhere at once, and that's very, very expensive. And so what we're going to be doing is wondering if there's some, first of all, do we need to look at, have a particular address live in more than one location? So we'll talk about why we might want that. And then we'll talk about sort of inexpensive ways to get almost the benefit of having it live anywhere in the cache without paying that expense of that huge parallel search to thousands of locations at the same time. The replacement strategy, so whenever there's a choice of where a value can live in your cache system, now you have, what should I get rid of? If the browser is caching web pages and you go visit a new one and it starts caching information from that new page, what should it throw out? It can't keep remembering all this stuff forever, partly because we run out of local storage, and partly as we remember more and more stuff, finding it becomes more and more expensive, and now, if you have a whole copy of the entire web on your machine, then it's like searching the web, and that's slow. So the idea is to maintain the speed. We want to keep what we have cached reasonably appropriate, and choosing what to throw away is really a question about, well, what are you likely to ask about in the near future, because I'll probably want to keep that. And then I want to throw away things that you'll never ask about again. So we'll talk about that, the engineering of that. There are some ways in which we can take advantage of particular attributes of modern memory systems, which is that they are actually pipelined. They have a long latency, but great throughput. And so the question is, what can we do in the design of our cache to take advantage of a memory system that has a long latency, but a great throughput? And then finally, we'll talk a little bit about the write strategy. When we're doing writes to memory locations, does that mean we have to wait for the slow memory to keep up with us, or are there some other strategies we can pursue?